Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be looking at the solution methodology of this wave equation, namely the first method being the method of characteristics. So we have so what we want to do is to use the method of characteristics and we assume an infinitely long bar. We assume an infinitely long bar where x is between minus infinity to infinity, that the length of the bar, and we assume no body forces, or we assume that f is completely zero in this model. So then we can further assume the initial conditions. The initial conditions u at x comma 0 is f of x, and partial t of u of x comma 0 is g of x, and from here I can find out the momentum equations. I can rewrite the momentum equation. The momentum equation, which is a 1D wave equation, this time it is going to be homogeneous, is partial t square minus c square partial x square u is 0, or we have that partial t minus c times partial x times partial t plus c times partial x of u is 0. And then we can possibly choose this first factor derivative to be partial r and the second partial factor to be partial s. So this is partial s. So what I have now is that from these two choice, we have partial r is partial t minus c times partial x, and similarly partial s is partial t plus c times partial x. And from here I see that I compare my derivatives of x and t. So what I do is, what we have is we are going to compare these two relations and we arrive at the following. So we arrive at that partial x partial r comes out to be minus c, and partial x partial s comes out to be c. So from here we have inverted our relation. So partial x partial r is this, and similarly partial t partial r comes out to be 1, and partial t partial s comes out to be 1, and we see that x is c times minus r plus s and t is r plus s. Right, okay. So then my r is 1 by 2c x minus ct, and s is 1 by 2c x plus ct. So we have found the variables with which we are differentiating, and now our original wave equation was partial r partial s of u is equal to 0. So from here I see that the relationship I get is u of r comma s comes out to be a solution of the form fr plus g of s. Now r and s are already known, so this is f of x minus ct plus g of x plus ct. Okay, and then we can find these two functions f and g using my initial conditions. So I see that from initial conditions I get that u at x comma t is half f of x minus ct plus half f of x plus ct plus 1 by 2c integral from x minus ct to x plus ct g of z dz. So this is the so-called famous D'Alembert's solution of the wave equation. People who have done some basic partial differential equation, basic courses, will be immediately familiar to this solution method, which is the analytical technique of finding the solution to the wave equation. Okay. So I got the analytical form of the solution in the form of the initial as a function of the initial conditions f and g. So let us look at an example of this method of characteristics. So suppose I have my initial conditions are u of x comma 0 is f of x and ut at x comma 0 is 0. We see that f of x is 1 comma 0 where x is between minus 1 to 1 and 0 otherwise. So we find the solution here. We find the solution to the momentum equation with linear constitutive relation. So here these are my initial condition and I can quickly deduce that my solution for the displacement u of x comma t is going to be half f of x minus ct plus half f of x plus ct, and the g value is 0, so there is no term associated with g. So now we see that these functions f is nothing but a rectangular wave. So if I were to plot f versus x, then we see that this is from minus 1 to 1. This is at, so we have from t equal to 0, we have the following relation. Okay, so from minus 1 to 1 we have the following relation. Okay, so from here I see that this is my initial condition f, which is a rectangular wave. So now this particular form of the solution u will be the superposition of two rectangular wave, one moving to the left and the other moving, well, this is moving to the right, and this one is moving to the left. Okay, so we see that the solution comes out to be this form, but to get a better idea we can try and draw this solution to see what is happening. So to see that, if we were to plot the solution, we see that the solution is from minus 1 plus ct to 1 minus ct, the solution is 1, and from 1 minus ct to 1 plus ct, the solution is minus 1 minus ct, right? And we see that from here I see that the solution u is, this is for the time when ct is 0 to 1, so for small times, and then for larger times we expect these rectangular waves are going to separate out and they will leave a gap in between. So we see that if we are for ct greater than 1, we find that the solution u comes out to be minus 1 minus ct to 1 minus ct, and this is the value equal to half. This is all value equal to half, and then similarly from minus 1 plus ct to 1 plus ct we have the following, and we see that we get the following. Okay. So then what we have now is that this is, so this is a solution for the various times. Now, just want to highlight the fact that the method of D'Alembert is only going to be applicable when we have infinitely long domains, or this is also the limitation of the D'Alembert's method. That is, this is for unbounded, applicable for unbounded domains only. Otherwise, for bounded domains, we have to use finite integrals, which is going to be severely restrictive form of solution, which is where we cannot use the general D'Alembert's method. Okay, so then we have the next method I want to highlight is the method of Laplace transform in solving this wave equation. Okay, so the method of Laplace transform method. So what is this method? Now the Laplace transform, let me call this as LT. The Laplace transform of a function u of t is defined as u of s is from 0 to infinity u of t e to the power minus st dt. And the inverse Laplace transform of us is given by ut is 1 over 2 pi I integral a minus I infinity to a plus I infinity of u hat s e to the power st ds. Remember here that s in this inverse Laplace transform is a complex number, and I have u, the function u is a continuous function. It's a C0 function, C0 of t. So u of t must be a continuous function. And we also want to highlight that this particular integral from a minus infinity to a plus infinity is the so-called Bromwich contour integral, which is the line integral on the complex plane along the vertical line. So this is the line integral on the complex plane, along the vertical line. So what we now have is that in this case the line integral is such that you have the real component of s is the integrating variable here, must be equal to fixed, and that fixed value is a. So this is an integration along the vertical line or along the imaginary, an axis which is parallel to the imaginary axis. So before we move ahead, let us now just write down or tabulate the Laplace and the inverse Laplace transform of some of the commonly known functions, which helps us to find the transform of the various functions we are interested. So suppose we have u hat s, we denote it by the Laplace transform of u, so u L of u, and the other is the L inverse of u hat. So we want to find the Laplace. So if we are given the Laplace transform of u, linear combination with v, we see that L inverse u is, for this function, is L of a of ut plus b of vt. Okay, so what it means is that the Laplace transform is a linear operator. It's a linear operator, so it linearly transforms. Okay, so then v hat s, u hat s is, so the Laplace transform of the product of two transforms, if we want to take the inverse, the answer comes out to be a convolution, which is v convolve with u, and this is defined as 0 to t v of t minus r u of r dr. Okay, and then s of u hat s is u prime. So s of u hat s, the Laplace transform is, the inverse Laplace transform is u prime of t plus u at 0, and then the inverse transform of 1 over s u hat of s is integral of 0 to t u of r dr. Right? We can continue this tabular form. Then for the transform e to the power minus as u hat s, this is also u of t minus a h of t minus a, where a is positive. And similarly, the transform of u hat of s minus a is e to the power at u of t, and then 1 by s plus a to the power n, we see that the transform is 1 by n minus 1 factorial t to the power n minus 1 e to the power minus at, where n is 1, 2, 3 and so on and so forth. And then the Laplace transform of 1 over square root s plus a comes out to be 1 by square root pi t square root e to the power minus at. And then the transform of 1 over square root s by square root s plus a comes out to be e to the power a square t times the error function complement of a square root t. And then the transform of 1 over s e to the power minus a square root s is 1 by square root pi t e to the power minus a square by 4t, where a is greater than 0. Okay, so these are some of the various transforms I have noted down from standard transform tables, which is very useful in finding the eventual answers, which involves inverse transforms and Laplace transforms. So for example, let us now look at some examples. The first example I have is a very simple example. Find the Laplace transform of ut, which is 1. As simple as that. Now, so the answer is u of s is going to be integral 0 to infinity 1 times e to the power st dt, and this is negative 1 over s e to the power negative st, where t is from 0 to infinity. Now, here we make a small stop and we say that what happens when we evaluate these limits, especially the limit at t equal to infinity. So the question is, what is the limiting value of e to the power minus st as t goes to infinity? And if my real of s is less than 0, I expect that this limit does not exist. This limit does not exist, right? So if the limiting value is less than 0, we get a exponential to some positive power. Taking the limit at infinity will blow up the limit, and hence the limit does not exist. So we must have, so for us to be defined, so u of s is defined, then it implies that real of s must be greater than 0. And also in that case, my us comes out to be 1 over s, that is when we plug in the limits. Okay, so we need to be careful when evaluating the Laplace transform, as that example has shown us. That is, we need to define what is the domain of s. Okay then. So then let us look at one more example. We want to find the Laplace transform of ut, which is given by e to the power minus t sine of 3t. And we see that ut, in this case us, is integral 0 to infinity sine of 3t e to the power minus s plus 1 times t dt. And if we do, again, to find the Laplace transform, we have to evaluate this integral, and this integral has to be done integration by parts. Okay, so we do that, we find that this is minus s plus 1 by s plus 1 square plus 3 square e to the power minus s plus 1 times t sine of 3t minus 3 by s plus 1 square by 3 square times e to the power minus s plus 1 t times cos 3t, and this is the limit at t equal to 0 to infinity, and this is also equal to 3. So when we plug in all these limits, we see that the limit turns out to be 3 divided by s plus 1 square by plus 3 square. Okay, so then let us now again look at another example where we have the function which is piecewise continuous. So the example that I have is, so this is my example 3. So ut is given by the following piecewise continuous form. So 0 to minus 1 if my t is less than equal to 1, and if my t is between 1 and 3, and if my t is greater than 3, we need to find us. We need to find us, and us is equal to, now we plug in this piecewise continuous function in the formula for transform. We get that this is from 0 to from 1 to 3, we have the range 2 times e to the power minus st dt, plus from 3 to infinity we have from 3 to infinity we have the range minus 1 times e to the power minus st dt. For limit between integration limit between 0 to 1, the ut value is 0, so we don't write the integral. We integrate this and find that the answer is the following: e to the power minus 3s plus 2 by s times e to the power minus s. So we find that so the question now is, so that was an easy problem to attempt, but the question now is the Laplace inverse of this u hat equal to u? Let us see what happens. So the question we are trying to now answer is, for let's say for this example, is the Laplace inverse of u hat equal to u? Does the inverse faithfully give back our original function? Let us see this by working out the example. So my inverse of u hat is negative 3 times L inverse of 1 over s e to the power minus 3s plus 2 times L inverse of 1 over s e to the power minus s, and we see that this is negative 3 h of t minus 3 plus 2 times h of t minus 1, right? Where h is my Heaviside function, h of t, h of x is my Heaviside function given by 0. So if x is less than 0, Heaviside function is 0, and if it is half, then x is half at x equal to 0 and 1 at x equal to x greater than 0, right? So at x equal to 0, we take the averaged value for x less than 0 and x greater than 0. So if we expand using this definition of Heaviside function, then we see that this L inverse comes out to be 0 if t is less than 1 and it comes out to be 1 if t is equal to 1, and it comes out to be 2 if t is between 1 and 3, and it comes out to be half if t is equal to 3, and finally it comes out to be minus 1 if t is greater than 3. So if we go back and look at our original function, the original function was 0 at t equal to 1. The original function was 0, and here at t equal to 1 the inverted function is 1. Similarly, the original function at t equal to 3 was 2, and here the original function at t equal to 3 is half, where half is the averaged value of 2 and minus 1, and similarly 1 is the averaged value of 1, 0 and 2, and that is the discrepancy that we are getting. So the conclusion of this entire exercise is that more or less the Laplace inverse will give back the original function, except at few points of discontinuity, except at finitely many points of discontinuity. Okay, so the conclusion is L inverse of u hat is u at all value for all t where u is continuous, but at jump points the inverse equals the average. The inverse equals the average of the jump in the function. So that is what we saw, that at the jump points the value was equal to the average below and above the jump points. Okay, so then finally we end our discussion with another quick example. The example that we have is u is 2 over s minus 3 by s square plus 4, and let us say we want to find u of t. So u of t is, we want to find the Laplace inverse of u hat. This is what we want to find. So the Laplace inverse of u hat is going to be the Laplace inverse of 2 by s minus 3 by s square plus 4, and this is going to be 2 of Laplace inverse of 1 over s using our linearity of the operator, minus 3 of Laplace inverse of 1 by s square plus 4. And again, if we use our Laplace inverse tables, we see that this is also equal to 2 minus 3 by 2 sine of 2t. So we can divide by so sine of 2t. So that is coming directly from our Laplace tables. Okay, so then let us now wrap up our discussion for this module by mentioning the fact that we are looking in our next discussion, in the next modular discussion, we will be directly looking at a particular class of material and try to discuss and derive the constitutive relation for that class, namely the class of viscoelastic material. And that will lead us to the conclusion of this entire course on SwayamPrabha, that is on classical mechanics. So thank you so far for listening. Thank you so much.